Hey guys, so in this video I want to start talking about springs and spring forces. Let's check it out. So when you push or pull against a spring with a force, let's call this force FA, an applied force, the spring pushes back. This is just Newton's third law, action-reaction. You push against something, pushes back against you. So the force of the spring will be the negative of the force that was applied on it. And again, Newton's action-reaction. That's why it's the same magnitude, but opposite direction. Okay, so this negative here means just opposite direction. So there's nothing new there. What is new is that this also equals to negative kx. And I'll talk about what kx is in just a second. Notice that there's another negative here. And again, that negative just means opposite direction. That negative is, you'll see this more later, is almost sort of a conceptual negative to remind you that it's an opposite direction. But in a lot of calculations, we'll just get rid of that negative to make things a little bit simpler. All right, so what is k and x? I'm going to start with x. X is the deformation that the spring will experience. So the idea is that if you push or pull against the spring will either be compressed, which means it's now shorter, or it will be stretched, which means obviously that it is now longer. But x is the deformation. It's not the actual length, but it's the changing length. So in springs, what matters is not how long it is, but how much longer or how much shorter it gets, okay? So x, you can think of it as the absolute value of the final length minus the initial length. The reason why it's the absolute value is because if you get a negative, we'll just think of it as a positive because the direction doesn't matter, okay? So for example, here I have this first drawing here. I have a spring attached to a wall. This green thing is sort of like a base that you can sort of drag on the spring. And if the spring here is just sort of left hanging there, it will have no deformation. It's the original length of the spring, x equals 0. We call this the relaxed position of the spring, right? The spring is just chilling, basically, without having been compressed. In this situation over here, this red dotted line here indicates the original length of the spring. And now I'm to the right, and that's because we're to the right of the spring here, of the original length. And that's because we pushed to the right with a force FA. If I push to the right, action-reaction of spring pushes back this way. Force of spring is this way. The gap between its original length and its new length, we're going to call, it's the deformation, we're going to call that x, okay? Now, since I have two different situations, I'm going to call this x1. We're going to use x2 for the bottom here. Here at the bottom, the spring was originally here, and then I pulled it this way, so my applied force is FA like that, and the spring will push back with FS this way, and the gap between its original length and its new length is deformation x, which I'll call x2. Okay, so that's how F and X kind of work. K is the spring, that's the second variable here. K is the spring's force constant. Okay, now there's actually multiple names for this. I've seen force constant, I've seen spring coefficient, I've seen stiffness constant or stiffness coefficient. But basically this is the coefficient of how hard it is to compress a spring. K has to do with how stiff or how hard to compress or deform in general a spring is. The higher the K, the harder it is to deform a spring. So for example, if you've ever played, I'm sure you have, with one of those pens that you push on it and the tip comes out. If you've seen inside of it, there's a small spring that allows this to happen. It's very simple. And it's a thin spring, and if you've ever played with it, it's really easy to squeeze and sort of stretch it out and moves very easily. So that spring has a very low K. Now, if you had springs, for example, at the bottom of an elevator shaft that are designed as a safety, if the elevator comes down falling, the spring maybe tries to hold the elevators in place. Those springs, we need them to be very stiff. Otherwise, the elevator would just crush them and they wouldn't do anything, right? So the K has to do with how hard it is to deform something. Real quick, the units for K are newtons per meter. And you can see this from the equation. Force is Newton equals kx. X is meters. So K has to be newtons per meter so that this equation is dimensionally consistent. Okay, so if you ever forget the units, you can just get it from the equation. by isolating, by leaving the x, solving the x, the k rather, leaving it by itself and seeing that the units, if you do unit analysis, you get newtons per meter. Or you can just remember that, okay? So force, one more point to talk about the force. Force of a spring is a restoring force, and that's really important. It's a restoring force. What does that mean? It's always going to, the spring is always trying to get back to its original length. If you pull the spring to the right, the spring will pull back left, and if you pull the spring to the right, to the left, it pulls back to the right, and if you pull it to the right, it pulls back to the left. You can see here that we went to the right of equilibrium, and the spring is trying to pull back to the left. Here we are to the left, and the spring is pulling to the right. So if you're to the right, you're going to be pulling to the left, and vice versa. Okay, so the spring is always pulling back. The spring force is always pulling the spring back to its original length, x equals 0. It starts relaxed. It likes being relaxed, and it's going to try to get back to its original length. The force is always opposite to the deformation, x. Okay, let's do a quick example here and see how this works out. I have a 1 meter long spring that is laid horizontally. So very similar to these diagrams here, with one of its ends fixed. So there's sort of a wall, and you have a horizontal spring. There's usually a little bar here, sort of a platform that you can drag the spring or sort of push a box against the spring against this, okay? So it has an initial length of 1 meter. As you do this, I want you to remember that what matters in springs is not the actual lengths, but the changing length. So it's not the length, initial length final, but the x, the changing length, okay? Now you're gonna come here and pull with a force of 50, which will cause the spring to stretch to a final length of 1.2 meters. And remember, what matters is not the length, initial, final, but the changing length. In this case, if I go from 1 to 1.2, the change is obviously just 0.2 meters. Okay, this is my applied force over here. And I want to know, what is the spring's force constant? Force constant is K. Your book or professor might use a different word, a different terminology instead of force constant, but it's the same thing, right? So what is K? Well, right now we only have one equation that deals with springs. We're going to have more later, but for now it's just force of a spring is the negative of the force applied, or the negative of Kx. The force applied and the force of the spring are the same. I'm just going to write a 50 here, and we're going to ignore the negatives. K is always a positive, so I can just ignore the negatives. You can think of it in terms of this negative cancels with this negative, but I think it's easier to just think in terms of the negative is just a conceptual negative. If I'm calculating a number, I'll drop the negatives and I'll get just positives. Okay, and that works better. X is 0.2 right here. And now we can solve this. K is 500 divided by 0.2, and you get 250 newtons. Newton per meter, rather. Okay. Now, typical values of K that you would see in physics problems are usually going to be in the hundreds, maybe in the thousands, but it's usually in the hundreds. Okay. It's usually not going to be a 2 or a 5 or a 10,000. It's going to be a few hundred. So that's generally, if you remember that, it might give you a little bit more confidence when you're solving these problems. But again, they could really give you whatever number they want, right, professors? So how much force is needed to compress it to 0.7? So I want to know how much force I need. So what is the FA needed to compress it to 0.7? Now, really important here is this word here, compress 2.7. Because I said compress 2.7, compress 2.7, means that my length final is 0.7, which means my x is 0.3. I started at 1, I'm going to 0.7, my x is 0.3. Had I said compress by 0.7, it would have meant that my x is 0.7. Or if I said a compression of 0.7, then it would also have meant that the x is 0.7. So be very careful here. Am I telling you how much it's changing by, or am I telling you what the final length is? Okay. In this case, we're dealing with this one here, but you have to be very careful. X is 0.3, and I want to know F. The equation again is Fs minus Fa equals negative Kx. I want to know what the force is, so I'm just going to say Fa equals Kx, drop the negatives. K, we're talking about the same spring, so K is 250, and the X is 0.3, so this is 75 newtons. Okay, 75 newtons is the force needed to get a compression of 0.3. This should make sense. A force of 50 got me a X of 0.2. A force of 75 gets me a compression of 0.3. A little bit more force, a little bit more compression or deformation, technically, right? In fact, this is 75 is 50% more, and this is 50% more. And that should make sense because this is a linear relationship. If one doubles, the other one will double as well. Okay, so that's it for this one. I want to quickly talk about vertical springs. So let's look at how this works. If you attach a mass to a vertical spring and let the mass come down slowly, I'm going to talk about this little detail here towards the end. But basically, if you put a mass, what's going to happen is the weight of the mass will stretch the spring. A spring, if left alone, won't self-stretch, right? So you need a force to make it stretch. In a situation like this object has a mass, it's being pulled down by the earth, has a weight of mg, and that mg is what's going to be responsible for pulling the spring down. And it will stretch the spring until they reach equilibrium. Now remember, equilibrium means acceleration equals 0, and that also means that the forces will cancel. Okay, so here's the idea. Before you put a mass here, this thing is at an x equals 0. It's relaxed. Because it's x equals 0, the force of the spring is also 0. 0 and 0. Okay, now let's go through this real quick. If you have a spring here, you put an object and you slowly let it fall. Once it falls a little bit, it's going to have a little bit of a compression or a deformation. It's going to stretch a little bit. If it stretches down, the spring is going to pull back up, trying to restore itself to its original length. Okay? And the idea is now you get a little bit of an F, a little bit of an X, and you get a little bit of a force of a spring. Let's play with some numbers here. Let's say mg is 100. Okay? You start with a force of 0 for this spring, but then you let it fall a little bit. Now the force of the spring, let's say, is 10. And you have 100 going down and a force of spring of 10 going up, right? Now you let it fall a little bit more. This 10 becomes a 20. It's still weaker than mg. So if you release, it falls a little bit more. And so on and so forth until this number is eventually 100, right? Why? Because this x kept growing, so this f keeps growing, right? And the x will keep growing. This thing is going to keep getting pulled down until these two numbers are the same. Once they both are 100, once the force of the spring reaches 100, because it's been deformed so much that it's pulling back with a full 100, now these forces are the same, they cancel, and if you let go, it doesn't actually stretch anymore because the forces cancel. Okay, so you can imagine that if you were to sort of graph this force, it would look like this, and eventually you reach 100 as your deformation gets bigger and bigger. This is sort of a force deformation here, right? So once you get to 100, they will exactly cancel each other, and because they will exactly cancel each other, I can say that kx, which is the spring force, equals kx, and mg, which is the gravity, will equal each other. And that's the equation that you need to remember. So they will reach equilibrium, and I will have that kx equals mg. Okay? This is what I like to think of as the vertical spring equilibrium equation. Okay? Now, that's not the official name of the equation, but I give it a name because I really want you to remember that every time you have a spring at vertical equilibrium with a little mass, it's just hanging there, stopped, this equation will be true. Now, this is only true if you let the mass come down slowly. So the idea is that you put a mass in here, and then you hold on to the bottom of the mass, and you don't just release it, you sort of let it come down slowly until it's reached equilibrium. Once it's reached equilibrium, if you keep moving your hand down, this thing will stay there, right? Now, if you just release, what's going to happen is, instead of getting to equilibrium, it's going to pass equilibrium and sort of go up and down. It's going to oscillate around the equilibrium point. That's not what we want. That's a future chapter. Okay, so for this equation to work, you have to let the mass come down slowly. My last point is that this setup also applies if you have a mass on top of a spring. So imagine I have a spring like this, and then you have a mass on top of it. If I release, the mass is going to do this, right? But if I release it slowly and just kind of let it slowly compress, eventually I'm going to release, and it's not going to move anymore. It works exactly the same. Kx equals mg still applies in that situation as well, because the forces are canceling just the same. Cool? All right, so that's it for that. I want you guys to do this practice problem. Remember the stuff we talked about. The x is the difference in size or length, not the lengths themselves. Remember that this equation applies if you have vertical equilibrium and all the other stuff we talked about. Let's try to do this and see what you get.